PN semiconductor diode in reverse bias configuration, you can see the terminals are as such that p-type region is connected to the negative of the terminal of the battery, and then you have the external battery positive terminal connected to the n-type region. This creates an electric field. Okay, the electric field is directed from N to P, and owing to this, since it's reverse bias, so you have uncovering of immobile ions on the N side. You have the positive group 5 impurity atoms, which are not contributing to the, of course, the current across the PN junction. And similarly, you have the group 3 impurity atoms, which are negatively charged on the other side. So the direction is as such, it's from positive to negative. Now what happens is when you apply the reverse bias external supply, the electric field is enhanced, the net electric field is enhanced, and it turns out that the depletion width increases. So there is more uncovering of the immobile charges. Okay, this is what we discussed in the reverse biasing of PN junction. Okay, now what happens is because of this reverse biasing, the majority electrons in the n-type region and the majority holes which are there in the p-type region are held back by this electric field. Okay, you see this the negatively charged electrons, they cannot sweep from n-type region and move from the n-type region to the p-type region because of the direction of electric field as such. Okay, because it's negative charges over here which are going to negative ions which are going to repel. The direction of electric field is as such, the force is established that is going to prevent holes from diffusing across the junction from P region to N region and then from N region to P region. Okay, this is the story of the reverse bias PN junction diode. Now, what happens is that when a reverse bias voltage is applied to a PN junction, the electric field in the space charge region increases. Okay, and this increases due to the external applied source VR. Now, the electric field may become large enough that the covalent bonds are broken and electron hole pairs are created. Now, it turns out that there are some minority carriers. I mean, there's in the p-type region you have electrons as the minority carriers, and then you have holes as the minority carriers on the other side in the n-type region. So they start diffusing. I mean, there's a very small saturation current due to these small minority carriers, and as you go on increasing the electric field, there is more widening of the depletion width, and the minority carriers, they may get enough energy that they start diffusing across the junction. And furthermore to it, what happens is you are giving enough energy to the electrons which are bounded in the lattice in the covalent bonds to break free from those bonds across the PN junction diode, across the PN junction, and they start increasing the concentration of such small minority carriers. And then there is a small current which is going to flow IS to the PN PN across the PN junction. So this IS saturation current starts increasing. Okay, and this increase because the electric field is large enough so that the covalent bonds are broken and the more electron holes are created, and the minority carriers, they start diffusing. So IS, the reverse saturation current, start increasing. Now the electrons are swept into the N region and the holes are swept into the P region by the electric field as given by the direction. So it generates a large reverse bias current. This phenomena is called the breakdown. So the breakdown is occurring because of the electric field which is strong enough to break the covalent bonds and break the electrons free in the lattice, which are the minority carriers, which are as well the minority carriers on either side, and they start diffusing from one side to another, resulting in a large reverse saturation current, IS. Now the reverse bias current created by the breakdown mechanism is limited only by the external circuit. So yes, of course, I mean, it depends on the magnitude of the supply. So if you increase the supply, you increase the electric field, and in turn you go on increasing more, rupturing more covalent bonds, and therefore the minority carriers and the diffusion of minority carrier increases across the junction, and you have more saturation, reverse saturation current. So if the current is not sufficiently limited, I mean, if you're not going to, for example, hold this out, you might want to, have a series resistor R that is going to reduce this current. You might burn out the device, okay, because of increasing reverse saturation current due to the heating effect. The PN diode might burn out. So a large power can be dissipated in the junction, and this damage would be due to the excessive IS square R current. that is the power which is going to be dissipated in the reverse biased PN junction. Okay, and if this current is going to increase further, you see the power dissipated in the device is going to increase, and this is going to create heating effect, resulting in the device burnout um, or permanent damage to the PN diode. Okay, so the current voltage characteristic of a diode breakdown are shown next in 1.21. So you see these regions are the breakdown region in which the reverse saturation current increases exponentially. So you see it's if you have a highly doped, let's say, PN diode, like for example in Zener diodes, you have high doped PN junctions, and you have very narrow. I mean, for a Zener diode, you have very narrow depletion width, which results in a very large electric field because the width is small. So the field is volts per the length of the junction. So the length of the junction is small. The electric field is again very large. So due to the large electric field, you can have a larger current, and that reaches at much lower values than the conventional breakdown voltages. So anyways, I mean, if you have very high doped PN diode, the breakdown voltage BV1 is smaller than BV2, which is the breakdown voltage for a low doped PN diode. Okay, because if you are going to have a very high doped PN junction, there's going to be more rupturing of bonds, and then there's more minority carriers diffusing. So due to the large number of minority carriers available across the junction, you're going to have a very large current, and that can be produced by low breakdown voltages. Okay, so reverse biased diode characteristics are shown over here for a low dot PN junction and a high dot PN junctions. The reverse biased current increases rapidly once the breakdown has occurred, and you might want to avoid these regions. I mean, this breakdown voltage for a typical PN diode could be of the order of let's say, could be from 100 to 200 volts or 50 to 100 volt. It basically depends on I'm talking of a typical silicon PN junction, but it depends on the fabrication of the device, number of concentration, how much doping has been done in the fabrication process of a diode, how much carriers are available, depend on the temperature condition as well. So it's a variable, but there is a peak inverse rating PIV which is associated with each diode, and that is the peak inverse voltage that you don't that you want to avoid if you want to avoid the breakdown of the device and burnout of the device. Okay, because this is a very large current. Okay, and that's going to burn out the device. So you have to abide by the peak inverse voltage rating of a diode. Okay, which is dependent on the fabrication of that particular device. Now, the most common mechanism by which the breakdown occurs, well, the physics of that is defined by the avalanche breakdown. What happens over here is that if the electric field increases, okay, which is from N to P type region, this is how it is directed in a space charge region. The diffusion of electrons, which are minority carriers on the P side, and then you have diffusion of holes from the other side. What happens is instead of okay, because of the E field, you have the breakages of the covalent bonds, yes, and there are more minority carriers, there is more diffusion. But what happens is it starts multiplying. It gets enough kinetic energy to bombard to collide with the silicon lattice atoms and knock out further electrons. Okay, so you have knocking off further electrons, and these further electrons they knock out more electrons, and this avalanche continues. Okay, so there's more knock of electrons. As electrons are knocked out from the silicon lattice, you have the holes. So there's more generation of electron hole pairs, and then both holes and electrons, once they have multiplied, they start conducting across the PN junction, and the reverse saturation current increases drastically. So the most common breakdown mechanism is avalanche breakdown, which occurs when the carriers crossing the space charge region, they gain sufficient kinetic energy from high electric field to be able to break the covalent bonds during the collision process. Now, the basic multiplication process is demonstrated in this figure 122, and the generated electron hole pairs can themselves be involved in the collision process, generating additional hole pairs. So the E field is not only responsible for rupturing the covalent bonds and increasing the number of electron and holes, but there's a multiplication process that goes on because of the sufficient kinetic energy of such minority carriers in the space charge region or the depletion region. They start colliding with the silicon atoms, and then in turn they multiply the electron and hole pairs, which again are contributing to the conduction of reverse current. Now the breakdown voltage is a function of the doping concentration in the N and P regions. So large doping concentration result in a smaller breakdown voltages and very large currents at low applied electric fields or low voltages. A second breakdown mechanism is the Zener breakdown and is a result of the tunneling of carriers across the junction. Now this effect is prominent at a very high doping concentration and results in a breakdown voltage of less than 5 volt. Now, Zener breakdown is usually less than your avalanche breakdown. So in the typical characteristic of the diode, I mean, Zener breakdown is going to occur much before than the avalanche breakdown. So for example, this is your VZ, okay, because of the high doping concentration of Zener diode as compared to the normal diode. So this is the breakdown voltage of a normal diode VB. VZ is occurring it occurs before. I mean, the Zener breakdown voltage required is less than the breakdown voltage required for a normal diode, because the depletion width of a PN diode, of a PN Zener diode, is much smaller than the normal PN diode. Okay, I mean, because of the small width of the depletion width, the electric field is large. The electric field EZ is large. Okay, and because of large electric field, there is a chances that the more covalent bonds are going to break. Okay, and then the breakdown voltages required for drastic increase in current reduces. Okay, because of the large doping concentration and smaller depletion widths. So the voltage at which the breakdown occurs depends on the fabrication parameters of PN junction, but is usually in the range of 50 to 200 volts for discrete devices, although breakdown voltages outside this range are possible in excess of 1000. So a PN junction is usually rated in terms of peak inverse voltage rating. Okay, so depending on the fabrication of the device, depending on the doping concentration, depending on the temperature condition, there is a peak inverse rating that you might want to avoid if you want to avoid the burnout of the device. So the peak inverse rating of the diode must never exceed in the circuit operation if reverse breakdown is to be avoided. Okay, so the diodes can be fabricated with specifically designed breakdown voltages and are designed to operate in the breakdown region. Okay, that's all.